So we're going to start to talk about internal combustion engines. Now, I'm sure we've all heard about internal combustion engines because they're in our most common mode of transportation, automobiles. Internal combustion engines are heat engines. The energy benefit is work or power, and the energy cost is heat or heat transfer rate. So internal combustion engines are a lot like Rankine cycles. But there's some differences too. So they're both heat engines, so we characterize them the same way. But for internal combustion engines, we'll assume that all the processes happen in closed systems, so we use a different version of the first law, and we'll assume that the working fluid is air, which is an ideal gas, so that's different than when the working fluid is water, like we saw in Rankine cycles. Now, before we get to analyzing these systems, it's important to think of some different terms. So here we have a piston that's moving up and down inside a cylinder. So the length of travel of the piston as it moves from bottom dead center to top dead center is called the stroke. So we have one stroke as this piston moves up and another stroke as the piston moves down. We'll talk about a couple different volumes in these internal combustion engines. Now, it's important to think about what we call the displacement volume. So here, if this system was open, let's say the exhaust valve is open, and the piston moves from bottom dead center up to top dead center, then it's this displacement volume that gets pushed out of the cylinder. So this is the volume that's defined between the top of the piston face at bottom dead center to the top of the piston face at top dead center. Notice that not all this volume is displaced. So we have the orange rectangle here, which represents the undisplaced volume in the cylinder. Often when we talk about engines, we'll talk about a compression ratio. So this compression ratio is always bigger than 1, and it's the volume at bottom dead center divided by the volume at top dead center. As we look at Otto and Diesel engines, we'll see that looking at the compression ratio will help us understand engine performance. Now, engines are moving at a particular speed, and if you look in your car, it will tell you the engine speed in rotations per minute, or RPM. So we might want to at least sometimes be able to convert that rotational speed to radians per second, and you can see how to do that in the calculation here. There's different types of engines, so if you're dealing with small engines, like you see on this dirt bike, you'll have a 2-stroke engine. So these engines undergo 4 processes, just like a basic Rankine cycle, but in a 2-stroke engine, all 4 of these processes occur in just 2 strokes. But as engines get bigger, we start to do these 4 processes in 4 different strokes. So each stroke represents 1 process. Here, we need 2 revolutions of your crankshaft to get 4 strokes. Another way to classify engines is how they ignite the fuel. So if you're looking at smaller vehicles, it has spark ignition. So I have a spark plug inside the cylinder, and based on the timing of the engine, the spark plug will go off at a particular time, which ignites the air-fuel mixture inside my piston cylinder assembly. So this is typically done on lower power vehicles. But as you get to higher power vehicles, you can ignite the air-fuel mixture in your piston cylinder assembly, in your engine, using compression ignition. So here, as you're compressing your air-fuel mixture, the temperature keeps going higher and higher. So if you compress your mixture enough, you'll get above the ignition temperature and you'll ignite the fluid just by compressing it. So this you see in higher power applications like buses and heavy trucks. It turns out that internal combustion engines are very complicated. Here we can imagine first an intake stroke where we have an intake valve open, we move the piston face down, and mass comes in to the cylinder. Then we close both the intake and the exhaust valve, and the piston face moves up, and we compress this air-fuel mixture. Next, both valves remain closed. We ignite the air-fuel mixture, and the piston face is forced down as the gas heats up and expands. This is the power stroke of the engine. Then, what happens, we have this spent air-fuel mixture. We've burned up much of the oxygen inside the chamber, so we open the exhaust valve, the piston moves up and forces the majority of the air out of the cylinder in this exhaust stroke. So in a 4-stroke engine, each of these processes happens in one stroke. So in internal combustion engines, we have more than one cylinder, and each cylinder is doing a different part of this process, so you get an even power distribution as you're running your engine. So these internal combustion engines are very complicated. They're not adiabatic. There's this air-fuel mixture which is being combusted, so there's chemical reactions. There's kinetic energy, which can be important here. Processes are transient, so they're not at steady state. The system is sometimes open and sometimes closed. So in order to get analytical solutions that we can work out with pens and papers, we end up making a lot of assumptions here. So we'll neglect combustion. We'll assume the system is closed for the whole time, that all the processes are ideal or reversible, that the working fluid is only air, and that air is an ideal gas, and sometimes we'll assume that the system has constant specific heat. Because we make all these assumptions, we have to remember that our answers are qualitative more than they're quantitative. But that doesn't mean that they're not useful. In addition to thermal efficiency, there are some other characterizing parameters we can think about. One of them is the mean effective pressure. This is the net work for one cycle divided by the displacement volume. If we took work as the integral of PdV, this is how you would get the work if the pressure was constant. We can evaluate how the engine is doing by looking at the thermal efficiency, how much of that heat that goes in turns into net work. To do that, we have to use the first law, but we'll assume the system is closed, so we use this version of the first law. The thermal efficiency is going to be the net work over the heat in, and if I make some assumptions, I can find the work for any particular process if I have a simple system, or the heat transfer for any process in a simple system. And I can use the ideal gas law because I'm assuming that my working fluid is air, and that air is an ideal gas. And because it's an ideal gas, I'll fix my states by assuming either variable specific heat using A22 or constant specific heat using isentropic relationships and relationships with specific heat. And then sometimes I might want to know the power. And here, to get from work to power, I have to introduce the idea that the engine is spinning at a particular rate. So now I have to use the calculations shown on this slide to find things like heat rate or power developed by the engine. When I do this, it's important to know if I have a 4-stroke engine, where I need 2 rotations per cycle, or a 2-stroke engine, where I only need 1 rotation per cycle. As with everything, calculations get a little bit more complicated when we're using imperial units. But the ideas here are still the same. When we look at the second law for these processes in our internal combustion engines, we have to remember we're assuming that each one of these processes are ideal or reversible, so we're not generating any entropy. Because of that, if we also have adiabatic processes, we can use our expressions for ideal gas processes that are isentropic. These equations are shown here on this slide. That's all I have for today. In the next couple of shorts, we'll look at how to evaluate Otto cycle engines and diesel cycle engines. Thanks for joining me on Thermal Shorts. I'll see you next time.